This conference will now be recorded.
Very good morning, students. We are continuing the chapter Rotational Motion and System of Particles. So today also we have picked up few numerical problems on this rotational motion from previous year's JEE paper. So the first problem you are seeing on the screen, it is actually from JEE paper 2019. Let us try to JEE main 2019. Okay, let us try to solve it. So this problem states that a circular disc of radius b has a hole of radius a, as you see in the figure. Hole is at the center. It has radius a. So you have a disc where the mass is situated in this annular region. If the mass per unit area of the disc varies, so mass per unit area of the disc varies as, we can just take this as, this is the mass per unit area varies. Okay, mass per unit area can be written as sigma. Okay, sigma varies as this. Then the radius of gyration of the disc about its axis through its center. Its axis means its axis about the center of mass and perpendicular to the plane of the disc. So how to solve this problem? So to solve this problem, let us just take a disk element and an elementary disk of radius r from the center, radius r. Okay, so you can see this is the disk. So I have mass between this region. Okay, if I just draw here, suppose this is the annular region. Originally this is the, sorry, so this is having radius a, this has radius b. I'm considering an elementary disk, okay, of radius r, okay, from center. So we have actually mass between the radius a and r for this elemental disk. So if we can find out the moment of inertia of this elemental disk, and then if we can integrate between the limit to b, we'll get the moment of inertia of this particular disk which has a hole of radius a. So let me get the mass of the elemental disk. Suppose it is dm. It can be obtained by sigma into the area of the elemental disk, that is 2 pi small r, and it has a thickness dr. Okay, this always will be having some thickness, so it is the dr. So basically I should have told you that I have considered a disk of radius r having thickness dr. So this is the mass. Now this sigma is varying with r, so we can actually find out the mass of the annular region of the disk. annular region of the disk How that could be done by integrating this limit between r is equal to a to b. If we integrate it, let us write this sigma over here. Sigma is sigma 0 by r, and this is 2 pi r dr. Okay, we have to integrate this quantity. So 0 to a to b, and this is c 2 pi sigma naught. This is a constant term, and then I have only dr over here because this r goes up with this. So finally, what the mass of the annular region is, that is 2 pi sigma naught into, so dr is r, so r we are taking limit b to a. Okay, a to b, so this is the mass, 2 pi sigma into b minus a, whole into b minus a. So what we have got, the mass of the annular region, for which I have to find out the moment of inertia. So I have shown you here the calculation. How do I calculate the moment mass of this annular region between a and radii a and b of the disk? So this is the calculation. I'll just, because of having less space, I'll do, I'll just use this space. Okay, I'll try to use this space to calculate the moment of inertia of the annular disk about its. So moment of inertia, in short, m dot I of the disk, of the given disk, can be then found out. I is equal to r square r square into r square into dm, right? R square dm. Okay, so this is r dm, and see, dm is what? Dm is r square. Dm is 2 pi naught into dr. Okay, I'll just keep it here, 2 pi sigma, since they are constant, and I can take the limit from here. A to b, limit of r will be a to b. Okay, so it is actually now a to b in this limit r square dr. Okay, so what we get is 2 pi sigma naught by 3 r cube, and if you put the limit, then it will give you b cube minus a cube. Okay, so what is the moment of inertia we have got? We have got moment of inertia 2 pi 2 pi sigma by 3 b cube minus a cube. Okay, this is the moment of inertia we have got. Now I hope you have already noted it down and you have understood this calculation, and I will just keep the mass of the annular disk here, just the value, and all other things I'll just strike off or erase, so that I can get some space over here. So mass of the disk, I'll just erase an elemental word. So you get mass of the disk as 2 pi sigma naught b minus a. This is what we have got. Now I have to find out radius of gyration. What is the way to find out radius of gyration? Let us say radius of gyration is k. Then mk square is equal to m r square by 2 for a disk, right? M r square by 2 for a disk, that we know. And or we can just, in this case what we have is, that is the I what we have got from here. So if we just go with this implies m k square is equal to 2 pi sigma naught 2 pi sigma naught by 3 b cube minus a cube. Okay, so what is k square? K square will be 2 pi sigma 3, and what is the m? M we can put it here. See, m will be coming here in the denominator, so that m I am putting from here 2 pi sigma naught b minus a. Okay, and here we have already b cube minus a cube. Okay, a cube, this we have. Further, look, what is b cube minus a cube? This algebraic identity you know already from your lower class 10th class mathematics. So we can write b minus a square plus ab plus b square. So this is a b cube minus a cube. Okay, so if we just put that there, then what we get? So if we just put this value here, so we get b minus a, and then we get b square plus ab plus a square. So this this will give you the answer. So this 2 pi sigma naught will go off. So you get b square plus ab plus a square divided by 3, and since this is k square, then what will be k? K will be I'll just say this part. So finally k will be square root of this quantity, right? So square root of b square plus ab plus a square divided by 3. So this is the answer, and you look, this B, option B will be the correct answer for this question. Okay, so this is how you have to solve this problem. So what we have done, so we have just taken an elemental disk of radius r and thickness dr. Okay, and then we had found out the mass of the annular region or annular region of the disk by integrating over the radius, okay, b to a, sorry, a to b, and then we have written moment of inertia r square dm, and from there we have calculated the moment of inertia, as you see, and moment of inertia and mk square, where k is the radius of gyration which we can equate to, and from there we can calculate k. So radius of gyration about the axis passing through its center. Okay, so finally we have got this answer. Okay, now we'll move on to the next question. So this question is also from 2019 JEE mains. JEE main 2019. So this question states that a stationary horizontal disk is free to rotate about its axis. Okay, like this. This is the disk about its axis, means axis which is passing through center of mass and perpendicular to its plane. Okay, that is its own axis. Okay, free to rotate about its own axis. When a torque is applied, its kinetic energy as a function of theta, where the theta is the angle by which it has rotated, is given by, okay, this energy is given by given as k theta square. This is not k theta 2, this is theta square, k theta square. If the moment of inertia if the moment of inertia is I, then the angular acceleration of the disk is moment of inertia. So let me just write down the rotational kinetic energy of this disk is given as k theta square. Okay, k theta square. And moment of inertia of the disk, okay, if the moment of inertia of the disk is I, then angular acceleration I is moment of inertia. And see the answer, we have to find out angular acceleration of the disk, and that is in terms of k and moment of inertia. Moment let me write in short, moment of inertia of disk about its axis. Okay. So see, we know rotational kinetic energy of any object can be written as half I omega square. Okay, so we know rotational kinetic energy can be written as half I is the moment of inertia, and omega square, and here it is given that to be k theta square. So what we can do now, see, we have to relate this to angular acceleration. So see, angular acceleration can be written, see, angular acceleration alpha can be written as d theta d2 theta by dt square, or in other way what we can do, we can write d theta. Let me show you how we can write again this term itself, dd theta of dd ddt of d theta dt. Let me write ddt of d theta dt. Okay, d theta dt. So this is d omega dt. Okay, so what we can do is, okay, let me write d omega dt. This d omega dt, how we can write, we can write d omega d theta into d theta by dt. Okay, see, is this kind of like crude way to think, like d theta, they will cancel each other, d theta d omega dt will get. So we can write this in fact as this d theta dt is again omega. So we can write, we have seen in the kinematics part, the b dv dx. So here also omega d omega d theta, where theta is the angular displacement and omega is angular velocity. Why I'm trying to write this in terms of omega, because we have been given this relationship. We have this relationship, so we can find out omega d theta. Okay, we have a relationship between omega and theta. So that's why I'm trying to kind of pushing this thing towards this. Okay, so what I know, okay, I'll write in short. So d theta, sorry, angular acceleration is omega d theta. So if somehow we can find out this d theta dt value and omega value, then we will be able to find out what is angular acceleration. Now we have got this relationship. Okay, so which I am writing over here again, half I omega square is equal to k theta square. Now if I write simply omega square, then it is 2k theta square by I, or omega is equal to, square root of 2k by I into theta. Okay, this is omega. Now what we'll do, from here itself we can just differentiating with respect to theta, both sides. So we'll get 2 omega d omega d theta is equal to 4k theta by I. So what we get from here is d omega d theta to be equal to 2k theta by I. So this is angular acceleration. Okay, so 2k theta by I. Look here, 2k theta by I. So this is the answer, 2k theta by I. This is the answer. Okay, in fact we don't require this, we require up to this. Okay, so this fourth option will be the correct answer for this question. Okay, so now we'll go to the next question. So this question is again interesting question. This is also from 2019, I hope. This is JEE Mains. This is again from JEE Mains paper. Yes, it is also, no, this is, yes, this is also from 2019 JEE Mains paper. JEE Mains 2019. So here you look, the problem is that a solid sphere and solid cylinder of identical radii approaches an inclined plane with same linear velocity. Same linear velocity, suppose they both have same linear velocity, that is v square. Okay, I'm sorry, this is v, linear velocity is v, same linear velocity v. Okay, now even though they have same linear velocity, they might be having different angular velocity depending on their radius, but here radii also same. So actually the rotational kinetic energy for both of them will be the same. Rotational kinetic energy for both of them will be the same. And see, for a body which is, okay, so here that is the information we get from this point, and both roll without slipping all throughout. It is moving while it is climbing up this arc or this inclined plane. It is actually moving or rotating without, sorry, or rolling. It is rolling without slipping. Rolling without slipping. Without slipping. So when cylinder or sphere, whatever it is, rolls without slipping, then the total rotational kinetic energy of such rigid bodies can be written as K rotational is equal to half m v square whole into 1 plus k square by r square. So where the k is gyration, radius of gyration. Here this k, radius of gyration, excuse me, and this capital R is the radius of this disc or cylinder, whatever. Now see the maximum, see according to conservation of energy, see whether it is linear motion or rotational motion, the energy conservation law will be followed everywhere because that is universal. So according to law of conservation of energy, we can write that the kinetic energy it has will be elapsed to reach up to the highest height, or at the highest point this mgh, see this as it is climbing up, the kinetic energy is getting converted into potential energy. So the maximum height, if it is h, small h, then the whole rotational kinetic energy will be converted into the potential energy. That's why I can write from conservation of energy this thing. Okay. Now look, this m goes, and anyway v is same for both. I have to actually find out the ratio of this to climb up maximum height. So the two climbs up maximum height h sphere, and this is h cylinder on the inclined plane. Then what will be the ratio of h sphere to the h cylinder? That is what is the question. So now see, h is actually, we have to find out the ratio. So h is directly proportional to 1 plus k square by r square. This part I can write. So look, for cylinder, what is k? For solid sphere, k will be k square, sorry, k square, that is the radius of gyration. See, m k square is equal to 2 by 5 m r square I can write for a sphere. So that is what I'll write in short. So m by, I'll write k square by r square is equal to 2 by 5. Sorry, 2 by 5. So k by r square is equal to k square by r square is equal to 2 by 5 for a sphere, and for cylinder, it is k square by r square. See, m k square here actually for a cylinder, the moment of inertia about its own axis will be mr square by 2. Okay, mr square by 2. So k square by r square will be half. Okay, so these two values if we put, look, I'll go to the next page. So h sphere is 1 plus k square by r square. So this can be written as 1 plus k square by r square is actually 2 by 5. So we get 7 by 5. And h cylinder is 1 plus k square by some k prime and r prime square. Anyway, r is same, but k will be different. So this is 1 plus half. Okay, this will give you 3 by 2. So if we find out the ratio sphere to the cylinder, So this is 2 by 3, so it will give you 14 by 15. So this is the ratio. I hope you have understood this problem. So 14 by 15. So option B will be the correct answer for this question. Now we'll move on to another problem. So this is also a very interesting problem. Let us let us uh, let us get the options of the answers. Okay, so look here. The answer is, the first option is 181 by 2 mr square. Okay, and option B is 19 by 2 mr square. Option C is 55 mr square by 2, and option D is 73 by 2 mr square. First of all, let us understand the question itself. So you have, see here, 7 identical circular planar discs. 7 identical circular planar discs, each of mass m and radius r. They are welded symmetrically as shown in the figure. It is in the horizontal plane. You can suppose the moment of inertia of the arrangement about the axis normal to the plane and passing through the point P. So this is the point P. So if an axis passing through P, then what will be the moment of inertia? So that you have to find out. So how to find out the moment of inertia? As you can see if we can just consider only one, and an axis pass through this point, which is perpendicular to the plane of this disk, then we use what is called parallel axis theorem, this plus m into d square. So kind of that we do. So in this case also we'll do similar thing. Look here, first of all, moment of inertia of each disk is how much? Or let me get the moment of inertia of this whole arrangement about their center of mass. What would be that moment of inertia? Let me write moment of inertia of a disk about its axis. That means axis passing through the center of mass. So that is given by mr square by 2, right? For a disk. So for this arrangement, what is the moment of inertia about the center of mass? So moment of inertia of the given arrangement is ICM about their given arrangement about own axis, about their axis. Okay, is ICM, that is actually 7 into mr square by 2. 7 mr square by 2 because there are 7 identical. Okay, now look, we have to find out the moment of inertia about this particular axis. Okay, so if you just think this, let me just think of this particular disk. So this, if this point is here sometime or here sometime, so this will be actually given as the moment of inertia total. So moment of inertia about their diameter would be how much? Moment of inertia about the diameter will be so moment of inertia of the about diameter. If we write the parallel axis theorem, then see, you can just think of so this P point to be, see, if I just consider kind of this is arrangement. Okay, this I have got already center of mass, the moment of inertia of the whole arrangement like this. About the center of mass we have got already, so that is 7 m square by 2, and I have to find a moment of inertia about this axis which is passing through P. So look, this moment of inertia of the given arrangement, moment of inertia of the given arrangement about the axis passing through P and perpendicular to perpendicular to the plane of the of its plane of the plane that's perpendicular to the plane. That's fine. So look now, when I have calculated a moment of inertia of this arrangement about the center of mass, so the whole problem now can be thought of this now. So I have a big sphere, a moment of inertia about its own axis I know. So the moment of inertia about this axis will be I is equal to ICM plus m into d square. D is this. So d is this means, so this is r and this is 2r, so 3r. So if you similarly, if you consider the p here somewhere or here somewhere or here somewhere, here somewhere, so see, I have taken this this starts from, this is center and this is a sphere of radius 3r. Okay, and we have actually, we have such 6 spheres. Okay, that's why you have to multiply. See, finally we will get moment of inertia so we have 7 mr square by 2 plus 6 into okay, so if you consider this to be, okay, this is not 6, let me write this as 7 into m r square is 3r actually. Okay, or we could do this thing. Okay, this is fine, I guess. So if we just solve it, see, 7 by 2 plus this is 7 into 9 and mr square, anyway this is common. So this would actually give you, this is 63 into 2. So this just a minute, I think there is a small calculation error. Okay, so actually what we have done is, up to this it is fine what we have done. So this is actually moment of inertia. I'm sorry, this would be moment of inertia of each of that. Okay, so this will be actually, see if I just consider up to here about this much, okay, of each pair, for each pair. Okay, I'll just restate the thing. Let me restate the thing. We have actually calculated moment of inertia about center of mass, okay, of each pair, sorry, each disk. But what about moment of inertia about this center, this center, this center? So this we have to find out. Okay, this will give you, what we have done here is, see, mr square by 2 plus m 2 r whole square into 6. This will give you moment of inertia about this axis. Okay, then I think this will be correct, because then it will be like this. You can consider this as a, this as a sphere, as I was telling, that has a radius 2r, and this is distance 3 r again. So then we can, so this will give you actually 55 by 2 mr square. Then finally this part you have to do. Okay, I'll summarize, and you might be a little bit confused. And it will actually give you, it will give you 181 by 2 mr square. Okay, I'll just explain once again. So what we are doing, we are getting moment of inertia of each disk about the center of mass. So whole arrangement will give you mr square by 2 into 7. Now we are calculating moment of inertia about this point. If suppose the axis, see, I have taken this disk and I'm calculating moment of inertia of this center of mass, like axis passing through this center of mass. Okay, this center of mass, this center of mass. So we have done moment of inertia about the diameter. id is actually this ICM plus m into 6 into m into 2r square. This is about diameter. Okay, so this I have written already, 7 by 2 mr square. So then we have got moment of inertia about the diameter of this segment. Okay, diameter in the sense, see, I'm just taking now this as a sphere. I'll just draw it. So far I'll just take this as a disk. Okay, this as a disk, and moment of inertia about this diameter I have got. Okay, about the diameter I have got. Now actually I have to get moment of inertia about the diameter, and then we have to take another axis, parallel axis, this. Okay, so finally what is the case? Case is this: moment of inertia of a disk which is radius 2r, and you have another r distance, another axis at distance r, and where the mass is also m. Okay, because this is another center. Okay, so this is the point actually. So we have got here so this will give you 55 mr square by 2, and so this is the axis p. I have to get moment of inertia. So ICM or whatever we have got here. So ID plus M 3r square. Okay, 3r square along with 7 of these are there. So that's how we get 5 by 2 mr square, and this is 63 mr square. This will give you this. Okay, all right, so today we'll stop it here. If you have further doubts on this particular problem, we'll discuss again next class before we start discussion of some other problems. So here the answer is this A. Okay, okay, if you have any doubt on this problem, we will again discuss on the next class, and then we'll move on to some other questions. Okay, so bye for today. Thank you for your patience.
This conference will now be recorded.